Thank you for joining Smart Science Educators. So today we'll be looking at the Grade 10 Physics Assessments, the Elites Assessments. This is the year 2026, and this is an assessment which was done by Grade 10 learners. Therefore, let's start by looking at the first question. The first question says, match the branches of physics in column A with the correct descriptions in column B. Therefore, the column A, here it is, and we have got column B for the description. So for the first case, we have mechanics, and for the case of mechanics, this is the study of motion, of forces and effects of forces on body. Therefore, being on number 1, its match is right there on column B as B. Therefore, this is how we match it, match with B. Then for number 2, on column A, optics. Optics, this is the study of light, vision, lenses, and mirror. Therefore, its match is on column B, number E, column B, number E, like that. Number 3, we have thermodynamics. Thermo means heat. Therefore, this is the study of heat, temperature, and energy transfer. On column B, it is right there at position A. Number 4, on column A, electricity, where electricity is the study of electric charges, circuits, and currents. On column B, this is number F, like that. Then column A again, number 5, magnetism. Magnetism is the study of magnets and magnetic fields. There is D on column B. D on column B. Then number 6 of column A. Number 6 of column A, we have acoustics. Acoustics, the study of sound and how it is produced and transmitted. Therefore, it is part C of column B as that. So question 2, identify 2 career paths in physics related to space science. Careers related to space science. This is the space. Therefore, we have the first one as astrophysics. Astrophysics or astrophysicist. Then career number 2, we have aerospace engineer. We have aerospace engineer. So these are the first 2, but we can add on and have another alternative answer as planetary scientists. Planetary scientists. So question number 3, define the term pressure and state its SI units. So pressure, by definition, this is the force acting on a body or surface, normally per unit normally per unit area, and its SI units, is Newton per square meter. Newton per square meter, or sometimes we use Pascal, Therefore, question number 4, state and explain two factors that affect pressure in liquids. State and explain two factors that affect pressure in liquids. For this case, we have the depth of the liquid, Therefore, how does the depth affect pressure in liquids? Therefore, pressure is directly proportional to depth. Therefore, pressure increases with increase in depth. Pressure and depth, they are directly proportional. Another factor number 2, which is density of the liquid. For this case, again, pressure increases with increase in density. Therefore, pressure is directly proportional to the depth of the liquid and also directly proportional to the density of the liquid. Question number 5. A cylindrical container has a base area of 150 square centimeters and is filled with water to a depth of 25 centimeters. Find the pressure due to water on the base. Therefore, you start by the formula and identify all the quantities which you've been given. The depth, and it is water. Therefore, you're going to use the pressure formula in liquids. Pressure in liquids, we have P to represent pressure. Therefore, pressure due to water will be height H multiplied by the density rho, then multiplied by the gravitational force G. And for this case, G is usually 10 Newton per kilogram. And for the case of density of water, density of fresh water is 1,000 kilogram per cubic meter. So insert all the values in our formula. Pressure due to water will be the height or the depth, which is 25 all over 100 to convert into meters, multiplied by the density 1,000, multiplied by the gravitational force 10. This gives us 2,500 Newton per square meter. Question number 6. Name 3 properties of a suitable hydraulic fluid. Remember, hydraulic fluid, these are fluid which is used in hydraulic machines. For example, hydraulic brake system. Therefore, this liquid should have the following properties. Property number 1, the liquid should be incompressible. Why do we use hydraulic fluid and not air? Because air is compressible. Then property number 2, we have it should have a low freezing and high boiling point. Property number 3, this liquid should not corrode parts of the hydraulic system. Now let's look at the next question. So the next question is number 7. Question number 7. So for question number 7 says the area for the larger piston of a hydraulic press is 4 square meter and that of the other piston is 0.05 meter squared. A force of 100 Newton is applied on the smaller piston. How much force is produced on the larger piston? So for this case we have to apply the principle of the Pascal's principle so that you're able to solve this question. From Pascal's principle, which states that when pressure is applied on one part of an enclosed liquid, it is transmitted equally to all other parts of that enclosed liquid. Therefore, we have force 1 all over area 1 is equals to force 2 all over area 2. Now our force 1 for this case, it is 100 Newton. Our area 1 is 0.05 square meter. Our force 2 we don't have. Our area 2 is 4 square meter. Now when you insert it in our formula, we'll have 100 Newton all over 0.05 square meter is equals to F2 all over 4 meter squared. So I multiply both sides of this equation with 4 square meter by 4 square meter. I remain with F2 as 100 Newton times 4 over 0.05. This results to an answer which is 8,000 Newton. So how much force is produced on the larger piston? It is definitely 8,000 Newton. Question number 8. Question number 8. In a hydraulic machine, the pistons of two connected cylinders have radius of 10 cm and 100 cm respectively. A force of 400 Newton is applied on the smaller piston. Calculate the force on the larger piston. Therefore, here again, applying the principle of moments. Applying the principle of Pascal's principle. Applying the Pascal's principle, we will have F1 all over area 1 is equals to F2 all over area 2. Therefore, and since this is a cylinder, area of a cylinder is given by pi multiplied by the radius squared. Therefore, if we take F1 to be 400 Newton, area 1 to be pi multiplied by 10 centimeters squared, then F2, which we don't have, then area 2 to be pi multiplied by 100 centimeters squared. Therefore, if we insert these quantities in our formula, we will have 400 Newton all over pi multiply by 10 square centimeters is equals to F2, which you don't have, all over pi multiplied by 100 square centimeters. Therefore, if I multiply both sides of the equation with pi times 100 centimeters squared, I remain with F2 being equal to 400 Newton multiplied by 10,000 all over 100. This gives me 40,000. This gives me 40,000 Newton. Therefore, calculate the force on the larger piston. Definitely, it is 40,000 Newton. So, question number 9. Question number 9. Differentiate between elasticity and brittleness in materials. Differentiate between elasticity and brittleness in material. So elasticity and brittleness, these two are mechanical properties of materials. Therefore, let's make two columns. We have elasticity and we have the second column for brittleness. So elasticity, what is it? Elasticity is the ability of a material to regain its original shape, the shape and size after deforming force is removed. After deforming force is removed. What about brittleness? This is the tendency of a material to break. Tendency of a material to break. Tendency of a material to break easily. With a little deformation. Tendency of a material to break easily with a little deformation force. Therefore, whenever you are differentiating or giving differences, they should be in line. They should be in line. So if you are talking of the definition, give definition for both cases. And again, we can use examples when giving their differences. Therefore, examples it includes rubber bands, and we have got steel springs. And for this case, examples includes glass and even dry biscuits. Dry biscuits. So you can use examples and all possible differences when giving differences, but remember they should be in line. If it's example, let it be example for both cases. If it's using their definitions, use definitions for both cases. Question number 10. The diagram below shows a force of 480 Newton hanged on a set of 6 identical springs. Each of the spring has elastic constant 50 Newton per meter. So question number 1. For this case, it wants us to determine the extension of the springs ABC. Determine the extension of the springs ABC. So ABC are in parallel arrangement. So the arrangement is parallel and they are identical. Since they are identical, we are going to use the Hooke's law formula, but with a little changes. Therefore, F is equals to N KE, where F is the force, the total force, N is the number of springs, K is the spring constant of each spring, then E is the extension, the total extension for that case. Therefore, E total for this case, it will be the total force F over N K. Back to the formula, E total will be the total force is 480. The total force is 480 Newton. All over the number of springs, it is 3, multiplied by the spring constant, which is 50 Newton per meter, as given from the question above. Now let's use our calculators and get the answer. For this case, I'm getting 3.2 meter. Therefore, the E total for ABC, it is 3.2 meter. So the second question, determine the extension of the springs DE. Again, these springs are in parallel connection and they are identical. Since they are identical, we are going to use the formula F is equals to N KE. F is the force, N is the number of springs, K is the spring constant, and E is the total extension. Therefore, the total extension for this case is equals to F all over NK. This is 480 Newton all over 2, because there are 2 springs, multiplied by the spring constant of each, which is 50 Newton per meter. This gives us, or this results on answer, which is 4.8 meter. Therefore, E total for D and E, it is 4.8 meter. Question number 3, the extension of the spring F. The extension of the spring F. Therefore, F is in series with the DE and ABC combined. Since it is single spring, it's just single, we are going to use the Hooke's law formula, or the law of elasticity formula, F is equals to KE. So from this you get E is equals to, making it the subject, E is equals to F all over K, which is 480 Newton all over 50 Newton per meter. This results to an answer which is 9.6 meter for this case, 9.6 meter. Then the total extension of the system. For you to get the total extension of the system, you sum all the extension from the above. Therefore, the total extension is equals to extension due to A, B, C plus extension due to DE plus or addition of the extension due to F. So this is 3.2 meter plus 4.8 meter plus 9.6 meter, resulting to 17.6 meter as the total extension for the whole system. Then the next question is the energy stored in the system. Therefore, for you to get the energy stored, E, the energy stored, E, for this case, we will use, we have got 2 formulas here. We'll use a half Fe, which will result to the total energy. Remember, energy is measured in joules. We'll have E is equals to a half multiplied by the total force, which is 480 Newton, multiplied by 17.6 meter. This results to 4,224 joules. Or alternatively, we can use the formula energy stored E is equals to a half Ke squared, where K is the total spring constant and E is the total extension. Therefore, we have to consider all the arrangements. So we had parallel for these two systems A, B, C. We had parallel arrangements in the system A, B, and C, and also D, E. So for the parallel system, we will sum. Therefore, these springs, we had 3 of them, taking the spring constant 50 times 3, then plus, sorry, we are not summing at this point, not yet there to sum. Then for the case also for DE, we're going to take 50 multiplied by how many springs? 2. So therefore this gives us 150, and for this other case 100 Newton per meter. And these springs are in series. So combined A, B, C, and D, E are in series with F, with the spring F. Therefore, to get the total extension, that's the total spring constant, K total will be the reciprocal of these. Have 1 over 150 or 150 plus 1 all over 100 plus 1 all over 50, getting the reciprocal, because in series total spring constant is given by 1 over K total is equals to 1 over K1 plus 1 over K2 plus 1 over Kn. In series, this is how it's calculated, but in parallel, we just sum. We add the spring constant of each spring. Therefore, using these quantities here, we get using these quantities we get 27.27 as the total spring constant in Newton per meter. Now applying the formula above, applying this formula here, we'll have E, the energy stored E, is equals to a half multiply by the spring constant, the total spring constant 27.27, multiply by the total extension squared, which is 17.6 squared. This results to This results to 4,223.58 joules. So this is an alternative way of getting the energy stored. It's almost close to each other. Looking at this value here and these are the value, they are almost close if you round off. So let's look at question number 11. Question number 11. Define the term temperature. Define the term temperature and state its SI unit as used in thermal physics. Therefore, temperature is the degree of hotness, or coldness of a body measured on a chosen scale. Temperature is the degree of hotness or coldness of a body measured on a chosen scale. Its SI unit is Kelvin. Its SI unit is Kelvin. Question number 12. Convert negative 273 Kelvin to degrees. So whenever you are converting a Kelvin scale to a degree Celsius scale, you subtract from the Kelvin scale 273. Therefore, for this case, we are having negative 273 Kelvin. If I subtract negative 273, which is the absolute temperature, it gives as negative 546 degrees Celsius. So this is how it's calculated. Whenever you're converting a Kelvin scale to a degree Celsius, you subtract 273. And case number 2 here, we are having a degree Celsius scale to be converted to Kelvin scale. So for this second scenario, you add 273 to the degrees Celsius scale. Therefore, for this case, we'll take 25 degrees Celsius, we add 273. This results to 298 Kelvin. 298 Kelvin as the answer for that question. So thank you for joining the Smart Science Educators, the home of physics, and welcome all. Remember to like, remember to subscribe, remember to share, and also comment on the areas, particularly on the CBE curriculum, so that you are able to learn more. So thank you.